Hello there, strokes suck. Every year about 15 million people suffer from strokes. Of those, there are 5 million who die and 5 million who are left permanently disabled. We're here to see if we can find any correlations between certain clinical features and risk of stroke. The dataset we are using is found by a reliable source on Kaggle, which shows information of about 5,000 hospital patients, their information, and their history of a stroke. In this project, we aim to use machine learning models, specifically the multi-layered perceptrons, to classify and predict the risks of stroke based on 11 clinical features. We will also do a brief analysis on the direct and complex correlation between said features. The project will be into 4 distinct segments: dataset analysis, the pre-processing, implementation, and training of the machine learning model, the evaluation and report. Dataset analysis. We first have to understand the difference between simple and complex correlation. Simple correlation is simply the correlation between two variables. If A changes, then B will change. Complex correlation is more complex. The correlation is between two or more variables. Let's use lactose intolerance as an example. A person eating cheese with no lactose intolerance will be fine. A person with lactose intolerance not eating cheese will be fine. Having those traits and having diarrhea are not simply correlated. No matter how much cheese a person eats, the chances of them having diarrhea is still dependent on another factor. Therefore, they will not have a strong direct correlation. However, if you eat cheese and are lactose intolerant, you will absolutely demolish your toilet. Those three variables have a complex correlation. Okay, that example was long but necessary, so I can explain this following point. Generated a correlation heat map using these following frameworks to show the simple correlation between all numerical values of the dataset. The higher the number, the higher the values correlate. You can see the diagonal axis is fully correlated because, well, you age. Simple direct relation between factors and stroke seem to be quite low, which is why we need to use complex correlations or machine learning methods to classify and predict these data. The solution we have chosen is the MLP. That is the multi-layered perceptron and not My Little Pony. The reason for this is because it is very effective at solving the problem at hand, which has high dimensionality and the ability to recognize complex relationship between data. We move on to the data pre-processing part. These are the main problems and tasks we have to tackle. Problem number 1 is irrelevant or useless data. The dataset contains quite a few useless rows. These rows are essentially rows containing missing information or unknown information. To prevent those from impacting our model, we simply just filter and drop those rows of data. Problem number 2 is that we have a skewed dataset. We have approximately a 20-to-1 skew on no stroke to stroke. This is a problem because our MLP has a high chance of just eating the loss by classifying everything as no stroke, still getting a very fake 95% prediction rate. The solution I have chosen is to oversample the stroke rows by essentially duplicating all rows with the stroke events, randomly changing a parameter or two by a very small insignificant amount like 0.002 post-scaling. Speaking of scaling, that's our third problem. We have quite a few numerical data columns, and each of them have their own ranges. The MLP model I have designed is loosely based on the old MNIST digit recognition model. We ideally want all our inputs to be within the same range of 1 to 0. For this, we use a process called min-max normalization. It essentially linearly squishes the top and bottom range of the data column between 1 to 0. For more information about that, please read my written report. I go into a lot more detail there. Scaling will help us achieve a better accuracy and a faster gradient descent, basically giving us faster training and better results. The histograms have generated the 3 main numerical columns and post-scaling. As you can see, important features such as distribution and frequency remain the same while only the range changes. The fourth problem we have is solving categorical data. We cannot feed emojis or text or non-numerical data to an MLP, therefore when we have columns like smoking history, we have to find a way to represent that as numbers. 2 popular solutions for doing this: hot encoding and ordinal encoding. Ordinal encoding essentially gives every unique category a number, then maps those numbers back into columns. The problem with this is that if there are no inherent ordering for each of these categories, it will be very inaccurate for the MLP to read its relation with other data. Brings us to our next solution, non-hot encoding. This essentially creates n number of columns for n number of categories. Depending on which category the data fits into, will be filled with a 1 or a 0, kind of like how a truth table works. This problem we have is splitting the dataset into training sets and testing sets. Split it into about a 10-to-1 ratio for training to testing. Now onto the machine learning section. There are 4 main sections of the MLP we have to consider and customize for our model. This is a visualization of the model I will be using. The numbers signify how many neurons or nodes are in that layer. Light blue, the activation functions between each layer. Activation functions. 3 main activation functions commonly used are the sigmoid, the hyperbolic tangent, and the rectified linear unit. The reason I chose to use tanh specifically is because there is a constraint within 2 values instead of we lose 1. I modeled this MLP similarly to the MNIST digit recognition model. 2-bound theory is that since the input and output are bound between a maximum and minimum value of 1 and 0, the hidden layer being bound by the same rule will grant some level of consistency and accuracy. Why tanh instead of sigmoid, you might ask? It's because tanh is 0-centered, has double the range, and tends to cope with the vanishing gradient problem better. And for more detail, read my written report. Third part we will be discussing is the loss function. The function I have chosen is the binary cross entropy loss. The reason for this is because this loss function excels at the binary classification problem. On top of that, it is highly customizable once you understand it to change sensitivities for either negative or positive, actively adding a multiplicative bias to the whole model. We see loss function is split into two terms, positive and negative term. The positive segment calculates the loss when the actual result is positive, y equals 1. Negative segment calculates the loss when the actual result is negative, y equals 0. For computer implementation, quickly a switch case statement is faster as it doesn't the additional computation that's going to be multiplied by 0 anyways. To view the loss, you can just multiply the positive or negative term by a constant. Propagation optimizer simply makes backpropagation and training faster. The Atom optimizer was chosen for my model, but in all honesty, stochastic gradient descent or even vanilla gradient descent would have worked. When we are done with explaining the choices made for the machine learning model, we are moving on to evaluation methods. We have three main ways of evaluation: confusion matrix, accuracy, and the F1 score. Accuracy is simply the prediction rate of the model, which is calculated simply by dividing the accurate predictions by the total number of predictions made. F1 score is a score calculated using two other metrics called the recall and the precision. Both these metrics are calculated using the confusion matrix. Confusion matrix is simply a 2x2 matrix describing all four positive states of a prediction. Here are our results. We achieved an accuracy of around 76% and an F score of 0.74. The plot also contains the evaluated confusion matrix if you want to pause and read it. To conclude, our MLP model has both negative and positive traits. Positive includes the fact that the model can be used as a preliminary diagnostic tool, check for your risk of stroke fairly accurately even with very limited information. This analysis also concludes that there are complex correlations between these clinical features and risk of stroke. However, we also have some problems. Accuracy isn't insanely high, and the reason for that is perhaps we need more data and more clinical features to make a better prediction model. So the rate of false positive and false negatives are very similar. We need the model to be more sensitive to positives. Lines are very important, and when it comes to diagnostic tools that essentially determines the risk of a life, we need to adopt a better safe than sorry mentality. The positive potential solutions for making this skew: modifying the loss function as detailed in the slides above. Another solution is to change the margins for prediction. An example of this is anything above a 0.4 is considered a positive. However, this may cause slightly less accuracy. So that's it. Thank you for listening. This module was fun. Please go read my written report for more details. Basically, all the diagrams were generated by myself, and the code included in the submissions and those that are not are just in the written report. So again, and goodbye.